Is the environment in a neutron star system conducive to life, whether it be whatever based, carbon, silicon, sulfur, methane?
There's a great science fiction story about this. Is it Bob Forward, I think, wrote about imagining what it would be like, what kind of entities could live on the surface of a neutron star. But it would certainly not be anything like we are used to, just because the chemistry and the chemistry is not behaving the way we're used to, and it's a very extreme environment in terms of the gravity, the magnetic fields, the temperatures are, temperatures are orders of magnitude greater than anything we see on Earth. So it's hard to rigorously say something in that circumstance.
Yeah, I mean, I guess they do look for not life directly, but in exoplanets they try to look at the spectrum of the light and try to guess whether maybe some of there might be the right chemical composition if they could resolve a planet, or they could look at the star and see if the planet's close enough to the star that maybe there's something plausible, like it's an Earth-like planet, they'll try to say sometimes, but it's all very indirect.
Yeah, you might be able to have sort of a planet harboring life orbiting around a neutron star, but it would have survived the star going supernova, and so even that would be a bit weird from our perspective.
How does the spin of a neutron star and black hole compare with the spin of Sol?
Do you know those numbers off the top of your head?
So the sun spins every kind of few weeks,
and
on a week-long
I think
time scale.
People aren't really sure how fast black holes spin. There's an upper limit of how fast black holes can spin. Normally we measure this in just some dimensionless number, like how many % of the maximum that it could be. In terms of how many times per second, I don't remember off the top of my head, I have to confess, but the number that I roughly remember is something like 1,000 or 10,000 times per second, depending on what kind of spin it has. So it could be much faster than the sun. Yeah,
the neutrons, if you're just talking about, say, how much time it takes for a little bit on the outer surface to go around, a neutron star can, some of the fastest ones are take a millisecond to just spin around.
Wow.
So it's the mass of the sun, the size of Fullerton, spinning around 50 times or more per second.
So it's like a galactic top.
Yeah,
very much. That's a good way to say it. And black holes are the same.
Only more so.
Only more so, yeah. They can spin, except it's much harder to know. The neutron stars emit this beam of light, and we can see that they'll pulse every so often.
So we can measure the spin of a neutron star quite easily, actually, because just the way we see them spinning around, and we measure a blip of radio waves every time they sweep past us.
But measuring the spin of a black hole is actually a really delicate thing. Black holes are black, they don't emit any light. When they spin, what that really means is that if you were to take, well, I don't know that it even makes sense to do it this way, but the space-time itself is sort of being dragged around, and so it's not so much, I don't know that it means something to like rotate this little diagram around.
If I had, like, say, a little particle that's falling in, so it's going straight in towards the black hole, if it was spinning, it would get kind of caught up and twirled around it as it falls.
It's like a swirling around the space and time around. Yeah, like a whirlpool.
So it's like when I hit that event horizon, it's just like me going to a really fast whirlpool, right?
Yeah.
Yeah, and so even if you started out heading straight in, the space and time will swing you into the rotational motion.
And like you can think of the horizon as a place where the whirlpool sucks you down so fast that there's no way to even like shout for help because the sound gets carried inside too.
Yeah. So if you want to know how fast a black hole spins, people can try to measure it. Now this isn't something that I work on much, but I've read a little bit about it. And the idea is a black hole's size changes depending on how fast it's rotating somewhat. And so they try to measure how close the gas, well let me say it's even more, try to say that again. So what happens is when there's gas falling into a black hole, it sort of swirls around it, but then there's some orbit when you get close enough when the gas just falls in and it doesn't keep orbiting around in a circle anymore. And they try to measure where that is, because where the matter can no longer spin around the black hole depends on how fast the black hole itself is spinning. And so this is a really delicate thing, and they have to model very precisely what kinds of gas it is and how the matter's, I guess it's how the matter is moving around.
Yeah.
But they try to infer it. And different people looking at the same black hole have gotten wildly different answers sometimes, depending on how they model everything.
Yeah. So it's hard to measure that.
Okay. So, what is the interaction between superfluidity and superconductivity inside a neutron star? Is there interaction magnetic or static electric? Feel free to talk about K, type 1 and type 2.
Well,
sorry. It was a question from the viewers, so, you know.
Okay, well, let's see. So, you know, I use sort of matter results from people that work on this, but this isn't directly what I work on modeling. So in a neutron star, you have this fluid of basically in the core you have this fluid of protons or mostly neutrons, some protons and some electrons, and then you have this crust, which is this sort of locked together heavy nuclei with electrons flowing around, and everything gets down to its kind of lowest energy states where you can have these kinds of superconducting and superfluidity phenomena. Let's see. It's not exactly like the kind of superconductor you see that you make in a lab. I'm not sure I'm not sure I can really give an answer that I'm sure about.
That's fine.
I can't, so
no, we can skip that.
Yeah.
Which brings us to my last question, because the next questions are just all from the viewers.
Okay.
Tell us about your childhood interest in science fiction. You first, Professor Lovelace.
Childhood interest in science fiction. Okay. So, I mean, I watched Star Trek: The Next Generation.
Yes, TNG.
Yeah.
And I still watch it. It's a little bit harder sometimes. They play fast and loose with the science sometimes, but just the base. It's not totally wrong. And I'll forgive a lot in science fiction if it can capture that interest, that sense of wonder that, you know, there's cool stuff out there to be seen. And Star Trek could do that sometimes. So I think, on the whole, I wouldn't say it's a bad thing, even if they'll show ridiculous things like little blobs of red goo creating black holes. That's not very realistic, like was in the last Star Trek movie.
Yeah.
But, you know, if it gets your interest in science,
Yeah.
then I'll forgive a lot. But I watched Star Trek. I still watch it. I liked it. But I also played a science fiction video game where you were trying to defend a space station from some aliens. And indirectly, this got me interested in black holes because this video game had a black hole you could fall into if you got lost. And I got curious about, well, what is a black hole? I'd never heard of it before. And that interest, off and on over the years, stayed with me, and I eventually started getting into black holes, and I was more interested in them later on. So I guess I always go around saying the moral of the story is that video games are a great use of your time. So that's what I'd say about that.
Yeah.
What about you?
Okay, so I guess a lot of my interest in science started out when I was a kid, and I used to read piles of sort of classic science fiction, like Asimov and Heinlein and
The Big Three.
Ben Bova, and you know, I really loved the elaborate world building, like the Heliconia and Ringworld, and
Yes.
you know, all this stuff. So that
Larry
was,
Niven and Purnell.
Yeah, like I just
I'll introduce you to
read
them
piles of
next
that.
time. So
Yeah, that would be really cool. Yeah, so I read a lot of that. I really got interested in the world building. I actually, you know, I wanted to be a science fiction writer for a while. You know, I actually won this award and I got a prize, and I used it to buy a computer, and then I used the computer to write a code that would randomly generate habitable worlds and tell you how long their years were and what color the sun was and just, you know, whether they had more earthquakes and stuff like that. And so I got, as I went along, I realized that I liked figuring out the model for the world more than I actually liked writing the story. I mean, I still like writing, but I really got, as I went, I'm like, okay, I really need to know all this science, I really need to know all this math, and then I got more and more absorbed in that, and I just decided I was going to be a scientist. and that's so it was really trying to figure out how people thought up these amazing configurations for worlds and planets and systems that brought me into this.
Awesome. These next questions are questions from the viewers specifically, okay? So if they're a little off kilter, I'm sorry. It's not mine.
We'll do the best we can, I guess.
Okay, first question from the viewers is, we're taught from grade school, and I actually talked to this person just last night through Skype. We're taught from grade school that nothing, not even light, can escape from black holes. Why then do we have polar jets emanating from their axis of rotation, celestial poles, composed of electron positrons and traveling at relativistic speeds?
So that's not coming from inside the horizon. So something like that, it's actually not very thoroughly understood. But you have stuff that's falling into a black hole that's spinning, and that's got some magnetic field, I think. And then there's the matter somehow gets accelerated onto the poles. But this all happens outside the horizon.
Okay.
Yeah, so that's the important thing to emphasize. It's true, once you fall inside the horizon, the surface of the black hole, light can't escape, neither can you. It's bad for your health. but think of it this way. Suppose outside of a black hole, if it's not spinning, the gravity is exactly the same form as if it were the sun or any spherically symmetric object. And so, just like you can have things that are stably orbiting around something, you can also have an object that might come in and swing around and then shoot back out into space, like a comet. And so but it doesn't even necessarily have to be in an orbit that comes back regularly. You might have something just sort of pass through, swing around, and leave. And so there's nothing inherently weird about objects, about matter coming out away from a black hole. It just has to do with how it falls in and how the gravity of the black hole, and if the matter is magnetized, then that also plays a big role. The magnetic fields play a big role in how the matter moves. But there's nothing intrinsically unusual about matter coming near a black hole and getting away. It's just the distinction you emphasize, that once you fall inside the surface, then you never get away.
And you can get quite close, and the powerful gravitational potentials around a black hole mean, for example, you could slingshot a comet crazy fast if it went very close to a black hole. So that's the kind of, if it gets close enough, it will gain a lot of energy, and this is through hand waving. There's various models and estimates and simulations that sort of show this. You can get this matter sort of falling in, leading to these jets coming out, but without ever going across the horizon.
But actually figuring out exactly how these jets get generated is a topic of ongoing research. The latest and greatest simulations trying to account for the curved space-time from relativity and the matter and the magnetic fields. This is all a very hot topic right now. And so in detail, we don't completely understand it yet. I think it's probably safe to say.
Concerning black holes, would there be all gravitational wave vectors emanating into the poles of the black holes? I'm sorry, I don't know if that makes sense, but it's
okay, so
just these are viewer questions.
Sure. So a single black hole by itself doesn't emit gravitational waves. If it's just sitting there by itself, rotating around, it just sits there perfectly still. If two black holes are orbiting each other, then gravitational waves get emitted out to far away to where the Earth might see them. Now, if the holes are far enough away that it still makes sense to describe it this way, you could imagine some tiny part of those gravitational waves falling down the other black hole's horizon. But really, when the holes get close enough together, it doesn't really, I mean, the space and time are curved, but you wouldn't really think of them as waves until you get farther away, usually.
I mean, maybe I'm not sure if this question is asking it, but when you have the system, it's radiating gravitational waves in all directions away from itself. And they're stronger along the axis, so along the axis of rotation, they're the strongest going up and down, and they're weaker going out to the sides, but they're present in kind of a peanut shape for the amplitude. So that could be what you're asking.
Yeah, I don't know. I wasn't quite sure.
I should have been, I should have talked to them last night, but I didn't get a response. So, at what distance would planet Earth be safe from a GRB generated by a black hole or neutron star collision?
depends on if we're in the way of the jet or not.
So, but what would be like a safe light year distance or parsec distance?
Well, jets can be many light years long, right?
Well,
They could be really
those are
long.
those are usually, you know, the. Well, yeah, I'm not sure exactly. It depends. There's the ones we've seen from the galactic merger type,
Yeah.
the active galactic nucleus. They have jets that are going, you know, thousands of light years.
Yeah, but those are in other galaxies.
Yeah, or millions of light
So,
years.
I mean, I think the point is any neutron stars or black holes that we know of that are close enough that we might be able to see them. They're far enough apart that away from us, it's not really a big threat.
Yeah, I don't remember the number right now. But I think, you know, we look at some of the candidate sort of, we know of no candidate system around us, like a supermassive star that might kind of collapse and maybe produce a type of GRB. But even if something happens in the neighborhood, there's the bright flashes we see are only from a small percentage of the directions. They're from these two axes, so it would have to be aimed right at us.
Oh, you're talking about the actual bore sight has to be like directed toward.
Yeah.
Okay.
So for it to be a more of a threat, but I don't remember the numbers in light years right now.
Okay. This is the last of the formal questions, and we'll take our final break after this. In a science fiction related question, can advanced Type 2 civilizations house a neutron star theoretically, and if they could, what would be the potential uses of it? I'm sorry, it's so simple.
Communications?
So if you built like a big space station around, I don't know about a neutron star, but certainly if you built one around a black hole, you could imagine using it as a power source.
Yeah.
You could drain the rotational energy by dropping in matter in the... One way to do it would be to drop matter in just the right trajectory so that you extract rotational energy. This is called
a magnetized neutron star is like a huge dynamo.
Sure.
So,
Wow.
So
I would think power.
It'd be hard to create one of these.
Right.
What energy scale was the Type 2 civilization?
Well, Type 1's what, like 16 to 18? 10x 16, 18? That's in the terawatt range, like watt range. Type 2 is 25 to 35, I believe. Depending on, of course, how big their soul is, you know.
Yeah, you'd be if you're handling a neutron star, you need to be dealing with energies greater than a sun.
Okay.
So, or maybe if you find one and you harness it, that's something else.
But then you'd also need pretty good technology just to get out into space because everything is fairly far apart on the size scale of people.